In the last video, we defined a linear combination of a set of vectors. And so we know how to use scalar multiplication and addition to simplify a vector. If we have a linear combination, if we have something like 2x1 plus 3x2, we know how to simplify that. However, if we're given a vector, can we figure out if it is a linear combination of a set of vectors? So here I have three vectors, a1, a2, and b. And I want to know if b can be written as a linear combination of vectors a1 and a2. In symbols, this would be written as x1 times a1 plus x2 times a2 is equal to b, where my x's are scalars. Substituting in my vectors, I have x1 times 1, negative 3, 4, plus x2 times 3, negative 4, 9 is equal to negative 8, negative 8, negative 4. I can use scalar multiplication and addition to simplify the left-hand side. That gives me x1 plus 3x2, negative 3x1 minus 4x2, and 4x1 plus 9x2. The right-hand side is still negative 8, negative 8, negative 4. Well, this is just a system of equations. So we can actually solve this. So here's the augmented matrix. We have the coefficients on the left, and then the right-hand side is our negative 8, negative 8, negative 4. And once we do our row reduction, this is what we get here to move it to row echelon form. And we can see that this last row is going to cause a problem and tell us that there's no solution to this. So this tells us that b cannot be written as a linear combination of the vectors a1 and a2. If we would have been able to get a solution, then yes, it could have, but since we didn't get a solution, it is not possible to write b as a linear combination of a1 and a2. So now we know that if we have a set of vectors, it might not be possible to write every vector as a linear combination. So our next question should be, how can we decide when it can be a linear combination of a given set? In general, a given vector b can be written as a linear combination of a set of vectors a1 through an, if and only if there's a solution to ax equal to b, where a is formed using my a1 through an as the columns. So let's go ahead and try to prove this. Let's suppose our vector b can be written as a linear combination of the vectors a1 through an, and I'm going to use LC to denote linear combination. Well, what this means, by definition of a linear combination, is that I can write this as x1 a1 plus x2 a2 all the way up to xn an equal to b, where the x's are our scalars. These are real numbers. Well, I can rewrite this as a multiplication. So I have all of my a's times all the x's is equal to all of the b's. And this is equivalent to my ax equal to b. And since we know the vector x exists, since this is a linear combination, that means this is guaranteed to have a solution. So that's the first half of the proof. It is an if and only if, so we do need to prove the other direction as well. So we start by supposing ax equal to b has a solution. Well, we can rewrite this matrix equation. We can rewrite ax equal to b as x1 a1 plus x2 a2 all the way up to xn an is equal to b. The ai's are going to correspond to the columns of the matrix A. And we know a solution exists, so we know that all of the xi's have to exist. And from there, that's just the definition of a linear combination. So therefore, we have the result.